Hello, everyone. Welcome to the first live session for the Essentials of Turbulence class. Feel free to ask any questions you might have, and I'll answer as best as possible. We'll wait for a couple of minutes until students start joining in, and you may ask your questions. So I hope you've been enjoying the class. All videos have been uploaded, of course, and you should be going through them one by one. A midterm exam and an end term exam would be coming up as well. So I hope you're preparing for that. My notes is all you would need to actually prepare for the exam. Some good references are, of course, Pope's book is what we followed mostly, but some good references are Davidson's book on turbulence, which I mentioned in the first lecture. Tenekis and Lumley is a good book, although as the chapters go along, it gets slightly more difficult to understand. But those are some really good books to read. The thing about turbulence is you will have to read those books again and again and again. It's with one read or maybe two reads, it just doesn't become enough to understand the material. While this is, I've been teaching this class for now several years, more than 10 years. And this is the 8th or 9th time that I'm teaching this class in different forms, of course. And every time I teach it, I learn something new. So it is that kind of class. Sometimes I tell my students, you take a turbulence class with one of the professors, and then if it is offered by another professor, take it. You learn something new. A lot of it, you will learn something new. So in that sense, reading notes or different books on turbulence actually gives you a different perspective. We've tried to follow Pope's book, but I've also, especially during the initial part, I've tried to follow, for historical context, I've followed papers. And a good introduction is given by Tinnitus and Lumley, so I followed that book as well. No questions yet, but we'll just give it some time. So you wouldn't have probably gotten to that point, but one of the first, the last couple of lecture videos involve working out problems. And that should also help you in answering a lot of different questions. But otherwise, questions are going to be based on, you would have done assignments by now. The questions are going to be based on the notes. So I would say read the notes thoroughly, try and understand each part of it. If you have any questions, obviously there's a forum through which you can ask, and we try to respond to them very fast, mostly within 24 hours. Otherwise there are these live sessions that are scheduled. This is the first one. I plan to have at least 2 more sessions, maybe even 3 more sessions like these that can help answer some of the questions, technical and also related to the exam. So let me know. So while I wait for the questions to come up, I can just try to see what we can do in terms of. So you should be able to see my screen now. While it's coming up, just a second. So if I share the screen, okay. So this was the first module. And if I let me just try and see why is. Okay. So this was we started with the despair and turbulence, if you remember, where I shared some very interesting quotes by scientists all the way from the 1900s, talking about how difficult of a topic turbulence is, right? And it's very interesting, right? How turbulence was and is considered to be one of the most challenging topics. So some very interesting quotes, just to give some historical context here on how complicated of a problem turbulence is, and it is challenging learning it, right? So the reason I started with that is to give you an idea. I mean, when studying a topic, of course, we have to know why we are learning it, but also to know, the depth of the problem, right? How there are several challenges to understanding this, and we have to know about the problem that we are dealing with. It's not a simple problem. It's a very challenging problem. In all of classical physics, this is considered to be, by many, the most challenging problem. By many, the most challenging problem in classical physics. And we looked at some very simple examples. We talked about those in detail. There's some very illustrative pictures are shown here on this slide, right? If you remember, forest fires, wingtip vortices, um, wake behind a submarine, cigarette smoke, due to the buoyancy, how it rises up and how it twirls and creates all these very interesting structures, right? So it presents some very beautiful pictures, but it's a very complicated problem to understand, right? And the fact that it is there in a lot of different applications around us makes it even more interesting, because in spite of it being all around us in a variety of different applications, our understanding of it still has limitations, and that cannot be said about a lot of other problems. It's one thing when it has a very specific application, right? And then, so not a lot of people are studying it, not a lot of researchers are studying it, but in the case of turbulence, it's there in a lot of different applications all around. That means researchers from different fields are studying turbulence in their own applications. And so, in spite of all that, there is a limitation in our understanding, and that is one of the most curious things in this research in turbulence. But there are reasons for it, right? There are reasons for why that is the case. I mean, you have a complicated problem that is there in a lot of different applications. Some of them are listed here, and this is just a subset of the list, right? I mean, you have it in biology, you have it in household applications, you have it in geophysical phenomena, you have it in oceans, you have it in galaxies, all around. So nature, engineering, all kinds of applications you have, and then you still don't have a full understanding, I would say. Okay. And of course, we've made strides in this problem, right? We've gone leaps into our understanding of turbulence, but still um, there are some holes in our understanding. And most of this first module covers why that is the case, right? Why that is the case. Why are there still holes in our understanding? So one of the aspects of turbulence that we constantly discuss through the class is this whole idea of um, multiple scales. So I show this through the simulation of a jet, actually an experimental image. So not a simulation, an experimental image of a jet. And it's a turbulent jet, of course. And you can see it looks beautiful, first of all. Secondly, it has this multiple structures showing up, multiple sizes of structures showing. Large structures versus small structures. And I've circled some of those, right? And no two structures, if you see, are identical. No two structures are identical. You have something where you have a really large structure, slightly smaller structure, even smaller structure, even smaller structure, going all the way to something like this as a circle there. And that's interesting, right? We talk about this one. This one here, a very small structure, a large structure here. So this aspect of having multiple structures is very interesting. So that means your resolution has to be good enough to capture both. And that brings in one of the biggest challenges in turbulence, isn't it? Obviously, this problem has been studied quite a bit in the 19th and 20th centuries. And but we still don't have a complete understanding. We move on in this lecture with showing some real images, large-scale images, satellite images. In this particular case, it's the Weddell Sea of Antarctica. And the island acts as a bluff body. What do I mean by a bluff body? Flow going, a body acting as an obstacle for flow. And you can see the image dimensions itself are huge. It's a satellite image, 240 kilometers by 320 kilometers. You can see that very interesting features are shown here, right? These are what are called eddies. As the class goes on, we see these eddies in the context of engineering. Here, we're showing some very satellite images actually showing those eddies. If you go to different scales, like in a turbulent jet, the picture that I showed earlier, you will see these eddies, except they're much smaller scale. These eddies are now, these eddies are 40 to 60 kilometers in diameter. The eddies that you see in a jet that are probably 10 centimeters in diameter of a nozzle, you will see eddies that are as short as probably 5 millimeters all the way to 10 centimeters. So that's the scale difference that we are talking about, right? That's the scale difference that we are talking about. And this, you see this in nature as well. This is another satellite image over another set of islands, and you will see this hairpin vortices that are being formed as wind, air is flowing over objects. And these are called the von Karman vortices. The von Karman vortices are exactly what you see when you have flow over a cylinder. Are exactly what you see in flow over a cylinder. So very interesting things that we see here. Here again, another example of swirling clouds. Again, von Karman vortices. So we move on by asking, ourselves, what is turbulence, right? What is it? And I had this picture of an elephant and six blind men, right? Touching different parts of an elephant and making their own interpretation of what they are touching. One guy says it's a fan, another says it's a snake, another says it's a tree, it's a rope, so on and so forth. So they make these interpretations about turbulence and basically what I'm trying to say is, especially over the last 100 years, more in the 1900s, going towards the late 1900s, there were definitions, understandings of turbulence that actually evolved over time. And as we'll see in this module, we now have a modern definition of turbulence, which was not there initially. So everybody has had their own interpretation of turbulence. And that's what I'm trying to illustrate through this picture. So descriptions of turbulence is what we started with. And, we had this picture, right? Da Vinci's painting describing turbulence. And believe it or not, this was the first description of turbulence. He described it through this small paragraph here, comparing it to that of long hair, And even then, this was obviously translated, but he described the flow of water through eddying motions. And it's so interesting, right? Even at that time, Da Vinci, he just put his observations down on paper. And that's what this is, isn't it? And he was just describing what we now actually describe turbulence as, He was talking about water has eddying motions, one part of it is due to principal current and the other due to random and reverse motion. Essentially, what he is describing as large scale versus small scales. That's exactly what he's describing. Okay. So much later, if we take a huge go further down in the years, you will see that we started to describe fluid flow and consequently turbulence by Navier-Stokes equations, right? A set of Navier-Stokes equations which are shown here, continuity and the momentum equation. Now, obviously, solving these equations is challenging. Analytically, they cannot be solved unless you make assumptions and simplify them significantly. So here, what we have is a set of non-linear equations that need some kind of numerical method in order to solve them. Exact solutions are available, but only for very simple problems. We talk about Reynolds here, right? Osborne Reynolds, he was the first one to basically investigate the transition from laminar to turbulent. And this was his experimental setup, right? At that time, there were no cameras to take images, so he basically drew a cartoon of what he was observing. He had this pipe through which water was flowing, and he injected a colored dye in there in order to visualize the flow. And as he increased the flow rate of the water, he noticed some very interesting pattern and change in patterns in the way the dye was flowing through this pipe. So what he did, what he initially saw was at a certain flow rate, obviously the die was smooth. Its edges were very well defined. But then as you increase the flow rate, he started to see the fluctuations in the die movement. Okay, some chaos, some recirculation, some fluctuations. The edges started to be more blurred. And then as he increased the flow rate even further, there was a vigorous mixing of the dye with the background fluid, as in water. Vigorous mixing. So here you will see that the dye sort of mixes completely with the water, as you can see here. And that's because of the turbulence. That was his observation through this experiment. So that enhanced mixing is one of the key aspects of turbulence. Enhanced mixing. And we spend a lot of time talking about this mixing. And so it's like diffusion, right? Diffusion in the traditional sense is molecular diffusion. It happens due to a molecular property called diffusivity. Turbulence, we call it enhanced diffusion, but it's not really diffusion. Diffusion happens because of diffusivity. Mathematically, it is a second derivative of the quantity, right? But then turbulence is not that, but it has the same effect. It has the same outcome as diffusion, as in mixing, right? So sometimes we call turbulence enhanced diffusion, although mathematically it is not. And physics-wise also it is not, but it has the same outcome. So these are some interesting pictures showing, the turbulent boundary layer, basically the atmospheric boundary layer. And you can see how the different structures are embedded here. Different scales are embedded here. Right? Again, another snapshot of a computer simulation looking at an exhaust jet. So scientists, obviously if we want to study turbulence, it'll be a good idea to define it first, right? What is it? What is the definition for turbulence? It started from the 1922s when, instead of defining it, scientists actually wrote poems about it, right? So Richardson from 1922 wrote something like this, basically describing an aspect of turbulence. Essentially, he's describing the energy cascade, what we define as the energy cascade. The energy cascade is the transfer of energy from large scales to small scales. And that's what he was defining. Von Karman, had another definition for turbulence. Heinz had another definition for turbulence in 1959. So all of this now, all these definitions, what happened was a lot of it described turbulence as a random phenomenon. And we had a lot of discussion on this, right? It's actually not random. And we spent a lot of time on this trying to see why don't we call it random? Because we are saying that turbulence can be described by the Navier-Stokes equations. There's nothing random about the Navier-Stokes equations. It's deterministic. You solve those equations, albeit by a numerical method, you will get an answer. You solve it again, you will get the same answer, provided the boundary conditions are the same. And I should say that, provided the boundary conditions are the same. So for a deterministic set of equations like the Navier-Stokes equations, how can they describe a random phenomena like turbulence? How can they describe a random phenomenon? That cannot happen, right? So that was the conundrum in all these definitions. So if you look here, Richardson he didn't use the word random, but he said big walls have little walls which feed on their velocity. So he was describing the energy cascade here. But if you look at Von Kang, he said turbulence is an irregular motion which in general makes its appearance in fluids. They flow past solid surfaces or when neighboring streams of the same fluid flow passed over or one another. Heinz later said it's an irregular condition and then said various quantities show a random variation. So now we know that the random variation is not really correct. Even Pope talks about it. It's seemingly random, but it's not really random. And why do we say that? Because of this whole thing, you're trying to describe it using the Navier-Stokes equations, which is deterministic. Then how can you describe it as random? So that's what we have in the slide, but none of the early definitions offer any precise characterization of the turbulent flow. As in, where, predicting under which conditions will it or not occur. So then the question is, this lack of precision here is possibly one of the reasons why we don't understand turbulence as well as we should, possibly. And if we don't know what it is, what can we say about the phenomena in a very quantitative sense? So this is what we've been addressing in this module, right? And then we finally go on to define turbulence, and this is the modern definition of turbulence as it stands. And it has not evolved beyond this point. It's a chaotic solution to the 3D Navier-Stokes equations that is sensitive to initial data and which occurs as a result of successive instabilities of laminar flows as a bifurcation parameters increase through a succession of values. So a lot of information packed in here. Firstly, we say that it is a chaotic solution. We don't use the word random. We say that it is 3D. We say that it is represented by the Navier-Stokes equations. We say that it is sensitive to initial data. So any change in initial data is going to cause it to change the solution. And that is what I was saying earlier, as in, if you solve the Navier-Stokes equations multiple times with the same set of conditions, with the exact same set of conditions, you will get the exact same answer. On the other hand, even if you change the boundary conditions or the initial conditions, even slightly, then you will get a different answer. So it is highly sensitive to initial data. And in addition, this definition talks about how it is a result of successive instabilities of laminar flows as a bifurcation parameters increase. What is that bifurcation parameter? The rounds. So this definition leads us to describe the attributes of turbulence. Okay, the different attributes of turbulence. The fact that it is disorganized, chaotic, seemingly random. It is non-repeatable. Large range of length scales and time scales. Enhanced diffusion or mixing. Three-dimensionality. Intermittence. And that is what we discuss a lot of it in this module. So this module offers that kind of description in introduction, where we talk about how tough or difficult of a problem turbulence is. How can we define turbulence? A lot of historical context and what are the attributes of turbulence. That is what this module covers. So I hope you're going through the notes and spending enough time reading this multiple times. Again, I haven't gotten any question yet, but then if you have any questions, feel free to let me know through the forum. We will have a few more of these sessions, which will be announced earlier, of course, and you can let me know your questions through those. So since we'll end the session here, and again, feel free to let me know if you have any questions. Thanks, everyone. Thank you.